Okay, today we start talking about the Banach and Hilbert spaces. We first study the Banach space. We're going to start with some basic concept and then build upon the existing knowledge to see what the Banach spaces are defined. So the first concept is the normed linear space. Okay, so the reason we're introducing the normed linear space is previously we have talked about the metric spaces. And once we have a metric space, we can naturally introduce a topological structure. We can define what is open set, what is closed set, what is compact set, what is dense, so on and so forth. But this information only, or this structure only gives us the topological properties of the space, but not any kind of computation related to it. So to study many important subjects in mathematics, we have to also consider the algebraic structure, so we can do some operations or computations on that. And this is the why we introduced the norm linear space. So first off, the linear space is something you have seen in algebra quite a while ago. And we're going to just review what the properties there. And we require our space to be not just to not just have a metric, but also to be a linear space. Okay, so we say that X is a set of elements, and let's say K is a field. Okay, and we specifically only consider the set of real numbers or the set of complex numbers. So the K is either R or C. Okay, we rarely use the C here, but just in some occasions, we talk about things in a more general setting, so we consider the field to be complex as well. But most of the cases in this course, we only work on the real spaces. Okay, so we have a set and we have a field. Then we call this X a linear space if we can do summation and the scalar multiplication on the elements in X. Okay. So the summation right here means that if I have two elements x and y, they're in X, I can consider the sum of them, which will be also in X. Okay, so the X is closed under the summation. And also, if I have any scalar in or any number in K, either real or complex, and we have X as an element in the space X, then the A times X is also in X. So it's closed under summation and scalar multiplication. But these two operations are not arbitrary. They have to satisfy the following statements, or the following properties. The first one is about the summation. There will be eight of them. The first four of them are about the summation. The summation is x plus y equals to y plus x. Okay, if for any x and y, so for any x, y, later on we'll also talk about z as well. and any, say, alpha A or B or alpha beta. We have the following. So first one is this: summation is symmetric. Second is, or I should say, commutative. The second one is x plus y, and then plus z is the same as you take the y and z first, and then take the sum with x. Third one is there exists a special element in x such that you add this element, which we call 0, to any element in x, you get the same element there. So it's x plus 0 equals to 0 plus x, and that is equal to x. The first one is for any x, it has an additive inverse, which we call negative x, which is also in x, such that the x plus its additive inverse, we know that from the first item is the same as the sum of these two in the reversed order, and this also equals 0, always equal to 0. Okay, so this first four properties means that the linear space is an abelian group under the summation. Okay. Right, that's the properties about summation. And then the next four, when we multiply some scalar to x and then multiply by another scalar, it is the same as we multiply the two scalars together first, then multiply to the element x. And there is a special element which is 1 in the field. So the 1 is in the field. When you multiply to x, you always get x. Seventh is if you have two scalars, you take the sum and then multiply x. It's the same, you multiply them to x separately. And then the last one is if you multiply alpha to the sum of two elements, it's the same as you multiply alpha to each of them and then take the sum. Okay, so these are all the 8 properties for a linear space. And the linear space is also called a vector space because sometimes the elements like this x, y, they're also called vectors. Okay, so linear space, vector space are the same. Right. So this is something you have seen in algebra. Now we're going to give some properties or definitions regarding linear spaces. Okay, the first definition is suppose we have two linear spaces, x and y. Okay, both are linear spaces. And I have a mapping T from x to y. And it is a linear mapping. In the sense that for any alpha, say for any alpha x, alpha is a scalar, x is a vector, x is a vector or element in the space, and any other scalar and any other vector. So I can call this x prime. If you take the mapping of this, you get alpha times tx plus alpha prime tx prime. So we can put parentheses here, but just sometimes make it cleaner if we do not. Okay, but anyway, this x prime, they're from x. This alpha, they came from the field K, and when you take a linear combination here, we know that it is still in X, right? So the linear, since X is closed under such operations, and then you take the mapping T and map it to a element in Y. So this will be in Y now, and it's equal to, you map the X and X prime separately. So this will be in Y. This will also be in Y, and then you take the linear combination still in Y. So that's a linear mapping. Okay, it just means that you take you apply the linear mapping to a linear combination like this, then you get a linear combination of the elements after the mapping. Okay, so if T is also a bijection or bijective, by this we mean that T is injective and also surjective. Okay, that means injective and also surjective. So what this two mean, you all know that injective means that if your Tx equals to Tx prime implies x equals to x prime. If this is the case, then we call it T injective. And the surjective means that if for any y in Y there exists some x such that the Tx equals to y, then we call the T surjective. So basically means that if you map x to, you take the image of x, they will be just equal to y. Okay, so that's what I mean by surjective. So if T is bijective, it's both injective and surjective, we call T an isomorphism. Then T is called an isomorphism. Okay, and in this case, we call x and y are isomorphic to each other. Okay, so when we say two linear spaces are isomorphic to each other, that means there exists some isomorphism between them. Okay, and apparently because T is bijective, sometimes it's also called one-to-one correspondence. So we know that the inverse of T exists, and also the inverse is a linear mapping. Okay, so the isomorphic basically means that they have identical algebraic structure in the sense of linear spaces. Okay. Okay. Linear subspace. Okay, we call Y a linear subspace if Y is closed under summation and the scalar multiplication. Okay, you know that geometric meaning is pretty straightforward. If, say, for example, we have x equals to R3 and the y equals to some plane passing through the origin. This is R3, which is my x. And if we have a hyperplane passing through our plane, passing through the origin, like this passing through the origin, then we can call this plane y, and it will be a linear subspace because it's closed under the summation and scalar multiplication. Okay, you take any two points or elements or vectors in y, you take the sum is still in y, and also you multiply any vector in y by a scalar is still in y. Okay, so that's a linear subspace. linear manifold. Okay, so it's just shifting this y to somewhere. Okay, in this case, we can say the x plus y. So this x is a scalar, is a vector in space x. So this is in x. The y is linear space, subspace we mentioned above, and this is defined to be all the elements or vectors like this, where y is in the space 1. So what this means is just the same thing. And instead of passing through the origin, this linear manifold will pass through the point x. Say for example, x is here, and then we just shift it to the new place. Okay, so it's called linear manifold. Linear independency. Okay, again, here if we say x1 through xm, so their vectors in the space x are called linearly independent if for a linear combination of this x, a1 x1 plus a2 x2 plus am xm. So the xi's are, they're just subset of x. There's some vectors in x, and then this a1 through am, they're scalars. Okay, so they're in K, in the field K. If this equals 0, it just implies that every coefficient is equal to 0. Then we say vectors are linearly independent. Okay, in other words, none of them can be written as a linear combination of the other. Okay, so these are equivalent, that. Okay, so this is only a finite number of vectors. Sometimes we also say a set is linearly independent. We say the set E, which is a subset of X. It could even contain infinitely many vectors in E, but we still can say that E is linearly independent if any finite subset, which means that you can actually extract some vectors from E and form a finite subset, x1 through xm. No matter how you form a finite subset of E, this finite subset is linearly independent. Then we can call E a linearly independent set. So we use the help of the standard linear independency to define the linear independency for an infinite set. Okay. Linear basis. Okay. So we say the E is called a linear basis. Linear basis of X. If E is linearly independent, as we defined above, and any X in any vector in X can be written as a linear combination of vectors in E. Okay, any elements can be written as a linear combination of vectors in E. Okay, and it is easy to show that if you can ever write an x in a way, in a linear combination of vectors in E, then the way of writing this is unique. You cannot find another set of vectors in E and they use a linear combination of them to represent the same x. That's not possible. Okay, and again, that's pretty similar to the proof for the uniqueness of linear combination of bases for finite dimensional spaces. Okay, so the idea is that if you can say you can write x as a1 x1, say let's say e1 plus an en, and this e1 through en are from the set E. At the same time, you can also rewrite x as a linear combination of b1, say f1, all the way to bm, fm. And you could have some repeated elements in E and F, but it doesn't matter. As long as you can write in this way, then you know that by subtracting the two sides, you get the zero coefficient for each one of them, and that implies that the representation is unique. Okay, so that's pretty standard, easy to do, and you can try it yourself. Linear span. Okay, linear span just means that all the possible linear combinations from a set. So let's say that E is a set of vectors, and the indices are called the set A. Then the linear span of E is denoted by span of E. It's all possible linear combinations of the vectors in E. So it's like A1 x alpha 1 plus dot 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 an x alpha n, where this a's coefficients are from the field, and this n is arbitrary. Okay, you can make linear combination using arbitrary number of vectors. Okay, that's the linear span. Okay. The last one is the sum, or Dirac sum. All right, so suppose we have two linear subspaces of X, then we can talk about the sum of them. Say the E1, the E2, they are both linear subspaces of X. Okay, so E1, E2 are both linear subspaces. And then the sum of them, just similar as before, it's just any combination of x1, x2, where x1 is from E1, x2 is from E2. Okay, so this is the sum of them. This is not particularly interesting, but a special case will be interesting if the E1 intersection of E1, E2 is only 0, because they are both linear subspaces. So they both at least they contain 0, right? Both of them at least contain 0. So when we take the intersection, it will contain 0. But if it only contains 0, then we say the 2. Then we denote this sum. The sum is actually called Dirac sum. So this is the sum. The sum of E1 and the E2. but this is called the direct sum of the two, of E1 and E2. Okay, and what's special about this is if you can write the two in this way, then any elements in the sum can be written in a unique way. Okay? So in the case of direct sum, for any x in E1, E2, there exists unique x1 from E1 and x2 from E2 such that the x is equal to x1 plus x2. Okay, so this is not true in general case, but if x1, E1, E2 only intersect at 0, then the decomposition of any elements in the direct sum must be unique. You must be able to write it in this way. Okay, because if not, then you will be able to say, I have x, I can write it as x1 plus x2. At the same time, it's also equal to x1 prime, x2 prime, where these two are in E1, these two are in E2. And then you can move the x1 prime to the left, x2 to the right. You have x1 minus x1 prime equals to x2 minus x2 prime. So on the one hand, this is in E1. On the other hand, this is in E2. Okay, so that means this element is equal to this element, and they're in the intersection of the two. But the intersection of the two is 0. So that means both of them are equal to 0. And that means x1 is just x1 prime. They're identical, and x2 is identical to x2 prime. So there is only one way to write x in this decomposition. Okay, so that's the Dirac sum. Okay, so these are some properties or definitions in the context of linear spaces. So now we want to integrate the two, or combine the two, combine the linear space structure and the metric space structure we discussed earlier. And we want to make them kind of consistent or useful so that we want them to want a space that has both algebraic structure and the topological structure to satisfy the following conditions. Okay, so now remember that we have a metric space. At the same time, the metric space X has a metric D, but also at the same time X is a linear space. Okay, so X is a metric space, which means that we have a topological structure of the X. At the same time, we want the X to be a linear space. It's a linear space. But the operations on them should satisfy the following. The first one is the D is translation invariant. We require the D to be translation invariant because right now, since I can do some summation on this X. So if, say, I only have the distance between 2 points, X and Y, then after a shift or translation of both points or both vectors, I should get the same distance. Okay, so no matter what X and Y, Z we're talking about, they should satisfy this. Okay, translate them, it will be the same distance. The second one is continuity in scalar multiplication. This means that if we have if we know the sequence xk converges to x, then multiplying the sequence by any constant or scalar, say a, this will converge to a times the limit, okay, for any a in k. And the other property is that if we have the ak converging to 0, so right now this ak is just a sequence in the field k, and this means that the distance between akx and ax is converging to 0 for any x, for any fixed x. Okay, so our scalar multiplication should be somehow consistent with the metric we defined earlier. So we need this metric and scalar multiplication summation to satisfy these two, and then in this case we can we will be able to derive a more useful concept, which we can do computation. At the same time, we can talk about topological structure on it. Okay, so that's the two properties. I want to make a few remarks. The first remark here is that, as you can see, the now when we talk about that this goes to 0, as k goes to infinity, it's the same as since we have the shift invariant, we can subtract both items or both arguments by x. Then we'll just get xk minus x, 0. Okay, in sequence to that, this is going to 0. Okay, so that's one remark we can derive from easily from the first item. Okay, this is always true. The second one is that if we have xk converging to x, meaning that this goes to 0. At the same time, yk converge to y, then this should imply the distance between, or the xk plus yk will converge to x plus y. Okay, so this is something new because of the algebraic structure we have on X now. And the proof for the second one is pretty easy. You just think, what is this? I want to show that this is converging, it's converging to 0. So just look at this, x plus y, right? And according to the first remark we made, this should be equal to the d of xk plus yk minus x plus y, 0. Right? We just do a shift translation invariant. We subtract x plus y from both arguments. And then we can see that it's xk minus x plus yk minus y, since we can do, the summation is communicative. Then we have this. And then this becomes the d of xk minus x. And I can subtract for each fixed k, I can subtract both arguments by yk minus y. So this will be y minus yk, or minus yk minus y. Okay, and by triangle inequality of d, this should be less than or equal to d of xk. I'm using another element 0. So this is just 0 negative yk minus y. Okay, and now you can see the first term. I can again add x on both arguments. I will just get dkx, dxkx, and the second argument I can add the yk on both arguments. I will get a yky. Okay, so this as a non-negative number is always less than or equal to this, and because this goes to 0, since both terms go to 0, I know that this one goes to 0. Okay, so I know that this goes to 0. Okay, so this is some easy properties we can see from the definition. Okay, so now you can see that the metric D here is more flexible. We can always measure the distance of two vectors by taking their difference and measure the distance or difference of them to 0. Okay, so like this, if I have x and y, it's always equal to d of x minus y 0. Right, we can always have this. So it turns out that what happens is, well, how to measure the distance of the two, it only relies on how far the distance, difference of them is from 0. So I'm going to define let's say, a special function called p to take this into account. So define the p as a mapping from x to non-negative numbers. I'm going to define it by px equals to distance of x and 0 for any x. Okay, so this p is actually integrates all the information we have on D, on the metric, since we can always measure, say for example, if I have any x and y, I know that's just D of x minus y 0, and by definition that's just p of x minus y. So we can always measure the distance between any two vectors in x, in the space x, using p. Okay, so you can see some very straightforward and obvious properties of this p. The first one is it is positive definite because as you can see, this is always greater than or equal to 0, right? And also the px equals to 0 if and only if the x equals to 0, right? Because it's equal to 0 means that this is equal to 0, and that means x just equal to x, just x equal to 0. Second one is that this is symmetric. The px is equal to p negative x. And that is because, again, by definition, the px is equal to the d of x 0, and that is equal to d of, if you subtract x on both arguments, you have 0 negative x. And because of symmetry of this metric, so it's just a negative x 0, and it's just a p of negative x. Okay. Subadditive, for any x and y, the sum, p of the sum of x and y is less than or equal to the p of x plus the p of y. And again, the proof is pretty straightforward because this left-hand side is d of x plus y 0. And this is equal to d of x minus y if I subtract y on both sides, both arguments. And then this is less than or equal to d of x 0 plus d of 0 negative y. And you know that the first one is just px. The second one is equal to d of negative y and 0. And that is equal to p of negative y. But because p is symmetric, so it's just px plus py. Okay, and that is the right-hand side. Okay, the fourth one is that if p of xk goes to 0, as k goes to infinity, this implies that p of axk goes to p of goes to 0 as well. For any a, any scalar. Okay, and again, this is pretty straightforward to show. It's just a property because this is this is just d of xk 0, and we see a property of the matrix or the when we integrate or when we combine the linear space and the metric space, with that the it should be continuous in scalar multiplication. So when we multiply a here, and this is 0, so when we multiply a here, then we just still get this conversion to 0 where x is always 0. Okay, so it's pretty easy to show. And last one is that if ak goes to 0, then p of ak x always goes to 0. So this last two are just applying or using the properties we said about the continuity in scalar multiplication. Okay, it's pretty easy to show. Now, the Frechet space. We're not going to use this a lot, but just as a reference, when we have a linear space, we have a linear space and we have a function p defined as above, then we call this space linear Frechet space. Or in general, it should be F space. And only when X is complete, then we say this space is a Frechet space. Okay, so what that means is the XP. So when we have X as a metric space, where the metric is actually can be included in this P now. It's a linear space and it has a metric space where the metric is characterized or determined by this P. We say this is called an F space, okay, or F star space for short. And if X is complete, so the complete means that every Cauchy sequence is convergent. And the Cauchy sequence, we need to use the concept of distance. And the distance is characterized by this P right here. Okay, so if X is complete, then XP is called a Frechet space. So to be specific, what I mean by complete is that if I have a sequence, C in X is Cauchy, meaning that for any epsilon, there exists some n, which depends on, depends on epsilon, such that the distance originally should be, in the metric space, should be dxk, dxk, or dxj less than equal to epsilon for any k and j greater than equal to capital K, right? But right now we just use the property of P. We can subtract xj on both arguments, and this is just equal to P of xk minus xj. So as long as this is less than epsilon for any kj greater than equal to k, then we say that this sequence is Cauchy in X. And if this Cauchy sequence always convergent in X, it means that it always converge to some point. Again, in the sense, the distance is in the sense of P. We call this Frechet space. So we'll just give a few examples, and then we're going to make a more special Frechet space in the called linear space, normal linear space or Banach space. So the Frechet space is more general. You just need this P right here to satisfy all these 5 properties. Okay, as long as the P is equipped, the X is equipped with this P, which satisfies all these 5 properties, then we call it F space or F star space. Okay, and then when it's complete, we call it Frechet space. Okay, just give a few examples. The first example, let's consider, well, probably the most trivial one is Rn, right? The Rn. And we can define the Px. X is a vector in Rn. We can define it to be, say, x1 squared all the way to xn squared. Take a square root, okay, for any n-dimensional vectors. Okay, That's the Fresher space. So it's pretty easy to check that the P satisfies all these 5 conditions. Okay, so that's the trivial one. And we can also consider the CM space. Say, for example, we have this M, which is a metric space. D is a metric on it. Let's say this is a complete metric space. Let's say a compact metric space. Compact metric space. And then we say the Cm is the set of continuous functions defined on M, right? What it defined F is a space of X. It's mapping from M to real numbers such that F is continuous. And then we say that you can define the P of U for any U in this CM space. We can define to be the maximum value of Ux, where X is from the space M. Okay, and this is actually how we define norms for that space. And this, if we call my P to be, and define my P to this norm, then it's also easy to verify these properties. So in this case, and also this is complete in this sense. We define above, so this is M, sorry, this is CM. P is actually Fresher space. Okay, and also the previous example, this is also a Fresher space as well for this. Okay, so these are two relatively easy examples, and we're probably more interested in such kind of examples in this class. And but generally, the Fresher space do not require anything other than these 5 properties. And in this case, we can actually see an example that is, the Fresher space could be meaningful or useful in some conditions. So this example is going to be this. So suppose we have a space X, S, and that is composed of the sequences in R. So say have X, that is defined to be a sequence. We write it X1, X2, so on and so forth. And each Xi is in R for simplicity. Let's just think it this way. So basically, S is a set of sequences, real sequences. Okay. Now we can definitely define summation. We can add 2 sequences just by adding their components or coordinates one by one. Okay, and we can also define scalar multiplication. We multiply the x by some scalar. That means multiply that scalar to each of the terms in the sequence. Okay, so this definitely is a linear space, and I can verify that all the properties we need for the linear space are satisfied. And right now we want to also show that this S has a P defined. So let's define how the P is defined right here. We're going to define the Px to be this. Okay, k from 1 to infinity, 1 over 2 to the k, and xk over 1 plus xk. So this xk is like the kth term in the sequence x. Since this x is something like that. So something like this. So this xk, which is the kth term in it. And take the sum. So it's basically kind of weighted sum of the terms. The way it's like this, and it's geometrically decreasing to 0. Okay, so then we can show that this is actually a Fresher space. Okay, so how do we show this? And remember that if we want to show it's a fraction space, we want to see that S is a linear space, which we have just said it's indeed a linear space. And then we want to show that this P satisfies all these 5 properties right here. And then finally, we need to show that this X is complete under the P. Okay, so we need to show this one by one. First, the S is a linear space, and we have showed this. This is pretty easy to show. You can check it yourself. And then we want to check, second item is we want to check that P satisfies all these 5 properties. Let's see all these 5 properties. Apparently, this the way we define the P must be greater than or equal to 0, right? So that's true. And also for any sequence X, if Px equals to 0, that just means every term is equal to 0 because you have a sum of non-negative terms. So if this is equal to 0, it just means every term is equal to 0, and that just means that every term like this is equal to 0. Okay, so it's positive definite. And it's also symmetric. You take the negative sign, you take a negative sign on all of them, and you get the same P, right? P value. So that's the second one. Triangle inequality. Okay, let's show that. So the Px plus y, this, according to our definition, should be the sum of this here. So it's sum 1 over 2k xk. You know the x plus y. This will be the sequence x1 plus y1, x2 plus y2, so on and so forth, right? So here we should have xk plus yk, 1 plus xk plus yk. Okay, so now I'm going to eventually show that it's less than or equal to p of x plus p of y. And what I know about this, should I write it off? So this is p of x plus p of y. I know by definition that p of x is just a sum, okay, from 1 to infinity, 1 over 2k, xk, 1 plus xk. That's for my px, right? Same thing for py, yk, 1 plus yk. Right, again, k is from 1 to infinity. So I want to show that this is less than or equal to this. Okay, I'm going to use a fact. If I have non-negative numbers a and b, I want to convince you that if a is less than or equal to b, greater than or equal to 0, then the 1 over a over 1 plus a is less than or equal to b over 1 plus b. Okay, and this will be easy to check because you just look at this one here. This will be I just multiply these two and then these two. I see if we get the inequalities, right? So it's a times 1 plus b is less than or equal to b times 1 plus a. If I can show this, then I will get that. And this, you can see when you multiply, when you break the parentheses, you will just have a less than or equal to b. So you can easily get that because this is the equivalent to a plus ab less than or equal to b plus ab. But this can be implied by that. Okay, so that's how I get to prove this. Okay, and I'm going to use that fact. Right now, I'm treating. I know that this one here is less than or equal to by triangle inequality of absolute values. I know this is less than that. So this is like my A, and this whole thing is like my B. Okay, so then I know that for each term in the sum, it's going to be less than or equal to the sum of their absolute values. Okay. Okay, so now if I can show that this is less than that, it will be enough. Well, how to show that? Let's see again, say I have a and b, non-negative. I'm going to claim that a plus b over a plus b is less than or equal to, what we hope for is that we have this part only, right? And then we have this, and also this one only, like what we needed here. Oh, sorry, here and here. Okay, and so we hope to get that. Okay, and this is pretty easy to show because this is equal to a plus 1 plus a plus b over 1 plus a plus b. But then you compare this and this, you see that the denominator here is smaller, so it potentially is larger, right? So this means this is bigger than or equal to that, and similarly this is smaller than or equal to this. Okay, that's why this whole thing is less than or equal to that. Okay, and now we're going to use that property right here. This shows that this quantity right here is less than or equal to xk or 1 plus xk, and also plus yk or 1 plus yk. Okay, so that's how we get that this thing here is less than or equal to this thing. Okay, so that's the triangle inequality that we proved. Now let's see the third one. Let's see the third one. If xk goes to 0, then axk goes to 0. Okay, so suppose p of xk, which is equal to, I should say in this case, x, I will not use k because I need a sequence xn. So the n is actually, for each n, this xn is a sequence. Okay, I would say that the xn is a sequence. First term is xn1, second term is xn2. Okay, so that's my xn. And then let's say if this one goes to some x, sorry, it goes to 0, I should say. If this goes to 0, so what this means is this sum, or k, x n k 1 plus x n k. Now this k is from 1 to infinity. If this goes to 0, I want to show that when I multiply this sequence by a constant a, it still goes to 0. So now the question is, if this one goes to 0. And apparently I just need to multiply a to each component, right? So at each term. So when I multiply that, I will get this. Okay, the question is, if I have this goes to 0, can I show that this also goes to 0 for any fixed a? Okay. Well, that's again, we're going to verify a property that for any AB over A plus AB, I'm going to show that, so the A, B are again greater than or equal to 0. I'm going to show that this is less than or equal to the A times B over 1 plus B if A is bigger than or equal to 1, or is less than or equal to this if A is Well, if a is 0, nothing to show, right? It's always greater than or equal to 0, so it's always less than or equal to that. So let's see, special case this, less than 1. Okay, this will be more interesting. But you can definitely add this, doesn't matter. Okay, so I want to show this, and this is pretty easy to show. For example, if a is bigger than 1 in the first case, if a is bigger than or equal to 1, then I know that a over b, a plus ab, I know this is less than or equal to a times that, so it's less than or equal to this, right? Sorry. It should be equal to, say I divide both. See, I divide let me just write it in this way. So it's a times b over b plus ab. Okay, and now the ab is bigger than equal to b. So that's why the denominator is bigger than or equal to a plus ab. It's bigger than or equal to 1 plus b. So that's why the whole thing is less than or equal to 1 plus b. Okay, so this is because of that. And that's for the case a greater than or equal to 1. A is less than 1. Again, if it's 0, it doesn't matter. If a is not 0, then we can see that a over b, a times b over a plus 1 plus ab, this is equal to what? Y, say, if it's not 0, then I can divide both of them by, both of the numerator and denominator by a. Now we've got a b, 1 over a plus b. So if a is less than, say less than 1, which is, consider this case. If a is less than 1, then 1 over a is bigger than 1, right? So that means this is less than 1 plus b. And this here is because 1 over a is bigger than 1. Okay, so in either case, we see this either is true or this is true. But if I combine the two, I just need upper bound for that. Then I know that 1 plus ab will be bounded by the maximum value of a and 1 times b, 1 plus b. Okay. And that's also something we're going to use here. I'm going to show that this right here is going to be less than or equal to the maximum of a. I can pull out this a as absolute value. The maximum of this times the xk n divided by 1 plus xk n. Right? So now I know that each term has this bound, and then I can move this constant outside of the summation. So it's less than or equal to the maximum of a1 times the sum, infinite sum I have here, which is the one we are familiar with, right? And this whole thing is just a px. So if px goes 0, this must go to 0 as well, since this is just a constant. Okay, so that's the second. That's the fourth property that we need to verify. Okay, and finally, the last one. Suppose I have a fixed x, fixed sequence x, then we have another sequence ak going to 0, then we want to show that the p of x, akx goes to 0. Okay, so now let's see that. The x, right now I read it as x1, x2, so on and so forth. And the ak convert to 0. I say ak goes to 0. So now let's look at the p of akx. And according to our definition, that would be just the sum for k from 1 to infinity. Let me use j here, not to be confused with the k. K is the index for the sequence in my x. The j is index for the sequence ak, for the scalars ak, aj. The p of ajx. is equal to, according to, or for any fixed j, we're going to multiply aj to x, so that would be that. The aj times xk over 1 plus ajxk. Okay, the question is, if we know aj goes to 0 as j goes to infinity, how do we show that this goes to 0? This infinite sum goes to 0. Okay, the trick here is to notice that first of all, when how should I say it? First of all, when the k is large enough, as you can see, when k is large enough, this anyway is less than equal to 1. Okay, so that means when k is large enough, I can actually take the sum, for capital K large enough, I look at the sum from k plus 1 to infinity of 1 over 2k. This should be bounded by 1 over 2 capital K. And I need this capital K large enough so that it's smaller than epsilon, or epsilon over 2, something like that. Then that means starting from the capital K, I can bound the tail of this whole thing, no matter what. Right? It doesn't matter what this aj is. It's always bounded by, it's always small enough. And then for the first capital K terms, I need to use the property that the aj goes to 0 as j goes to infinity. I want to show that is also small for a large j. Okay, so that's the trick. So if I write this formally, that means for any epsilon greater than 0, I know there exists some k which is dependent on epsilon only, such that the 1 over 2 capital K is less than half epsilon. So I want half epsilon, eventually I'll get epsilon as my bound. Okay, and then this K only depends on epsilon. And I also know that there exists some J well, this J will depend on epsilon and K. But eventually it will just depend on epsilon because K depends on epsilon as well, right? So I can just write this J epsilon such that when I look at the first capital K terms, I still want to bound it. And in this case, I know that the for the first capital K term, since the sequence is given, the sequence right here is given, right? So I know that up to capital Xk, these terms are fixed. The first capital terms, K terms are fixed. So I will be interested in, I know that this is less than, I would say, the maximum term for the xk, let me see this, 1 less than equal to k less than equal to this. So this will be a fixed number since the x is given here. So this is a fixed number. If my aj goes to 0, then I know that for j large enough, this aj times this, which is a constant, will be less than equal to, say, half epsilon, less than half epsilon, for any j greater than equal to capital J. Okay, because my k was determined first, and then I can determine my capital J below such that the aj times the maximum of xk, where, as I said, k is bigger than 1, less than equal to capital K, this will be less than half epsilon as well for any j greater than equal to capital J. Okay, so I have k and j chosen in this way, And then I can see that the P of AJX is equal to the sum AJXK 1 plus AJXK. Then I'm going to split the sum into the sum of the first capital K terms, and then the other terms, which is from capital K plus 1 to positive infinity, 1 over 2K, AJXK, or 1 plus AJXK. Okay, and now I'm going to use the property we just showed. This one is less than or equal to 1, no matter what, right? Because it's something divided by 1 plus our numbers, so it's less than or equal to 1. So that means that the whole thing here is less than or equal to the sum k from k plus 1 to infinity, 1 over 2 small k. And this is equal to 1 over 2 to the capital K, because this is a geometric sequence. On the other hand, I know that this first term, because the denominator right here is greater than or equal to 1, so that means this whole thing here is less than or equal to aj times xk. Okay? Right? So that's why this thing is less than or equal to aj times xk. But now you combine there are only capital K terms. And I know that this must be less than or equal to the aj times the maximum of them, because each term is xk, but each xk must be less than or equal to the maximum among the first k terms. And then sum 1 over 2k. K is from 1 to capital K. Okay, I know that. And in this case, you can see that I show that when j is bigger than or equal to capital J, this one is less than or equal to half epsilon. And this is always less than 1, right? Because this is a 1/2 or 1/4, so on and so forth. We know that this must be, the infinite sum is equal to 1, but this partial sum must be less than 1. But anyway, if I have this less than 1 epsilon, half epsilon, and this less than or equal to 1 even, I can have the whole term less than epsilon over 2. And the second term is less than, I know that when k was chosen so large, I know that this is less than half epsilon. So the whole thing will be just less than epsilon. So I know that when j, for any epsilon, when j is large enough, this is less than epsilon. That's how we show that it is it satisfies the number 5 as well. Okay, the number 5 right here as well.